Okay, hi everybody. Let's finish up our discussion of Chapter 5 and mathematical induction by looking at some problems, or a problem involving the Fibonacci numbers. There are more problems at the end of the textbook for you to do on your own. We'll get lots more chances to work with induction, so this isn't the end of the induction story, but it'll be the end for now. Okay, so Fibonacci numbers. This is a picture of Fibonacci. He was a 16th century Italian nobleman who invented Fibonacci numbers looking at the reproduction of rabbits. And if you're interested, you can look on Wikipedia and read more about him. They're very famous, and you've probably seen them before, and they're constructed in the following way. It's given by what's called a recursive formula. So you define the first two Fibonacci numbers, f1 and f2, to both be 1. And then from then on, the next Fibonacci number, f sub n, is the sum of the two preceding ones, f sub n minus 1 and f sub n minus 2. So if you start with 1 and 1, then the next Fibonacci number is 1 plus 1, which is 2, then 1 plus 2, which is 3, then 2 plus 3, which is 5, and 3 plus 5, which is 8, and 5 plus 8, which is 13, and 8 plus 13, which is 21, and so on. You get the idea. So it's an infinite sequence of integers, starting out 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and 89, and so on. The golden ratio is a number that the ancient Greeks were interested in. They came across it in the following way. I mean, the reason I'm bringing up the golden ratio is because it's actually related to Fibonacci numbers. So this will be a little bit of a slight digression. So suppose you draw a rectangle and you cut off a square, the big square. So here's your original rectangle, and then this is a square. And here you have a smaller rectangle. And the ratio of the width to the height of the rectangle is said to be the golden ratio if the proportions of this smaller rectangle are the same as the proportions of the original rectangle. By proportions, I mean the ratio of the width to the height. So it turns out that ratio, the ratio which makes that work, which is called the golden ratio, is the number 1 plus the square root of 5 over 2, which is about 1.6. And it's this larger of the two roots of the quadratic polynomial x squared minus x minus 1 equals 0. For our purposes, this geometric interpretation doesn't make any difference, but if you want to see an entertaining little video, I learned about this from the video Donald Duck in Mathmagicland back in elementary school. If you Google it, you can find this on YouTube, Donald Duck in Mathmagicland. If you skip ahead to about the 7-minute mark, you'll see a discussion of the golden ratio and a little bit about Fibonacci numbers if you read between the lines. So I highly recommend that. The connection between the Fibonacci numbers and the golden ratio is that if you look at the ratio of successive Fibonacci numbers, so remember the Fibonacci numbers go 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. And if you look at the successive ratios, so 1 over 1, 2 over 1, 3 over 2, 5 over 3, 8 over 5, and so on, where I've taken each Fibonacci number over the preceding one, that's where this fn plus 1 over fn comes from. And if you look at the limit, it turns out these ratios approach a limit, and the limit that they approach is the golden ratio. And that's what we're going to prove as an application of mathematical induction. Just to maybe help convince you of this fact, here's some data. So these are the Fibonacci numbers 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on, up to 987. And in this column, this is the ratio. So this number over this number. So 1 over 1 is 1, 2 over 1 is 2, and so on. And as you go down the list, you get here to 377 over 233. You get 1.61802, and then Down here it's 1.61803, and you can check with your calculator that this is very close to 1 plus the square root of 5 over 2. So maybe that helps to convince you that this is true. So how do we prove this? Well, we actually prove a simpler identity, which doesn't involve any calculus, which is here that if you take, so again, fn plus 1 and fn are a pair of successive Fibonacci numbers. And if you take fn plus 1 squared minus fn times fn plus 1 minus fn squared, you get plus or minus 1. It alternates, plus or minus 1. So here's a little test. If you take, if your successive Fibonacci numbers are 3 and 2, then you get 9 minus 2 times 3 minus 4 is minus 1. And then the next two Fibonacci numbers are 5 and 3. You get 25 minus 15 minus 9. That's 25 minus 24, that's plus 1. And then the next two Fibonacci numbers are 8 and 5, and you get 8 squared minus 5 times 8 minus 5 squared, which is minus 1, and so on. And so you see that the signs alternate. And if we can prove this polynomial identity, then we're going to get this fact about the ratio of Fibonacci numbers as a corollary. And the reason is, if we take the equation and we divide through by fn squared, so divide both sides of this equation up here, that one, by fn squared, we get fn plus 1 over fn squared minus fn plus 1 over fn minus 1 equals minus 1 to the n over fn squared. And now what happens is we go, as n gets large, well, fn goes to infinity, right? The Fibonacci numbers get bigger and bigger and bigger and bigger. So this number here gets smaller and smaller and smaller as the Fibonacci numbers get bigger. And so this ratio gets closer and closer here. This ratio, fn plus 1 over fn, gets closer and closer and closer to a root of the polynomial t squared minus t minus 1 equals 0. So it converges to one of the two real roots of that quadratic polynomial, but because fn plus 1 over fn is bigger than 1, the Fibonacci numbers get bigger, it must converge to the golden ratio, which is 1 plus square root of 5 over 2. So the result about the ratio that we want comes from this fact about this polynomial relation among Fibonacci numbers. And that's what we're going to prove by induction. And actually, it's not a very difficult proof using the kind of arguments that we've done so far inductively. So first we check the case where n is 1. So we're looking at f2 squared minus f1 f2 minus f1 squared. And f2, so that remember that f2 is 1 and f1 is 1. So this is 1 minus 1 minus 1, which is minus 1. And n in this case is 1. So that checks out. Now we assume inductively that this holds for the nth Fibonacci numbers and for fn and fn minus 1. And the statement in that case is that fn squared minus fn times fn minus 1 minus fn minus 1 squared is minus 1 to the n minus 1. And the power of minus 1, just to check, comes from the term with the minus sign. So if the minus sign here is n minus 1, then we should have the n minus first power of minus 1. And now we have to look at the next step, which is fn plus 1 squared minus fn plus 1 fn minus fn squared. That's here. And the standard trick for all these Fibonacci problems is we substitute the relation that defines fn plus 1 and rewrite it in terms of fn and fn minus 1. So here we have fn plus 1 squared. That's here. Here we have fn plus 1 fn. And here we have fn squared. And we expand that out. This part here becomes fn squared plus 2fn fn minus 1 plus fn minus 1 squared. This term here becomes minus fn squared minus fn minus 1 fn. And we still have our minus fn squared there. Now we count up the terms. Here you notice we have plus fn squared minus, here's a plus fn squared, here's a minus fn squared, here's a minus fn squared. Altogether, that gives us minus fn squared. We have a plus 2 fn fn minus 1 here, and we have a minus fn minus 1 fn here. So that leaves us with a plus fn minus 1 here. And we have an fn minus 1 squared here, which has been left alone with a plus sign. So we have plus fn minus 1 squared here. And if we pull out a minus sign, we get minus fn squared minus fn minus 1 minus fn minus 1 squared. But this right here is our inductive hypothesis. So this right here is equal to minus 1 to the n minus 1, and we have a minus sign in front of it. So altogether we get minus 1 to the n. And so we have a nice proof by induction of this relationship among Fibonacci numbers, which give us this limiting formula that the connection between the Fibonacci numbers and the golden ratio.